Thank you so much, Hassan. Hi, everyone. I'm very excited to be here and present my research. So today I'll be talking about the role of machine learning in electronic design automation. And most of this research was done during my PhD at University of Minnesota. I just started as an assistant professor this January. So hoping to build on this and continue in a little bit different directions towards computer architecture and green machine learning training. But for today, I'll be talking about the role of ML in electronic design automation. So my research is in this area of EDA, or electronic design automation, which is an area that builds algorithms or software to design chips. For decades now, chips have been growing in complexity. We started at having tens of transistors on a chip to today having billions, if not trillions of chip transistors. While Moore's law has been responsible for this exponential growth in complexity, an unsung hero has been electronic design automation tools. EDA has enabled us to move away from manual design of circuits and layouts by hand to automatically designing, optimizing, and analyzing large circuits. It's been one of the key reasons we see all these growing trajectories here. I like to use this cartoon representation to demonstrate the role EDA has played, where EDA itself is this antra called Dolly, which has allowed Moore's law and software to grow in complexity while being able to sustain the compute and energy demands of several high performance applications today. However, with the end of Dennard scaling, things have become much more hard for Moore's law to sustain. Yes, the number of transistors on the chip is still growing at that exponential complexity as shown by this orange trajectory here, but the number of useful transistors that actually contribute towards an increase in frequency haven't been growing with the same rate, showing the slowdown in the frequency speed. So there has been a significant challenge to make things more complex. The advent of high compute demanding tasks such as AI have made things a lot more challenging. For example, the complexity of machine learning models has been growing exponentially towards a path of better accuracy. This picture here shows that since 2012, that was the year ImageNet had its success, AlexNet had its success on the ImageNet dataset. The amount of compute used in training the largest AI runs has been increasing exponentially with a 3.4-month doubling time. Since 2012, this metric of the amount of compute required in training large AI models has grown 300,000 times. So bringing that picture from my last slide here and aligning the time axis, even though the y-axis is not the same, my message here is that previously Moore's law had a 2-year doubling time, which was assisting us in keeping pace with these software demands. However, there has not only been a slowdown in Moore's law due to Dennard scaling, the end of Dennard scaling, but there has been this advent of AI. So if you thought this gap, called as the design capability gap, was bad, just take a look at this gap AI has created. We need systems that are far outside today's capabilities to be able to sustain the demands AI has made. That brings me to the big picture goal of my research, is to develop, is to answer this question that says, can we develop significantly better EDA tools that can both keep Moore's law afloat and overcome this design capability gap while also helping hardware keep pace with these growing demands of software for both an ML or even non-ML compute heavy applications. So to understand what challenges exist today with EDA tools or why the semiconductor industry in general has prevented us to go on keeping up with that exponential growth in demands, I'm going to use this GPU as an example. So let's take a look at this GPU. It's an NVIDIA GPU. It has about 54 billion transistors. It's one of their largest GPUs. If you think about what resources it takes to design a chip like this, well, it takes a set of engineers, time, and money. If you think about those resources, and if you think about any of the world's complex problems we have, those are the same kind of resources we need. Gather a group of smart people together into a room, throw in some money, and give them sufficient time, they can come up with fantastic solutions to very complicated problems. It's no different with this GPU. Then what exactly is the challenge? Well, with the advent of AI and this demand for high performance, there have been the development of chips like these. This is one of the world's largest chips with 1.2 million transistors, and it's highly optimized for AI. It's over 50 times larger than the chip on the left, 100 times more number of transistors and AI codes. Yes, the complexity has increased when we move to left and right. And if you think about it, what kind of resources does it take to design a chip like this? Well, it's not very different from the GPU here, except that it's this a lot more of the same kind of resources. Soon you will see that this is not a very sustainable business model, not even for large design houses, and it's very inaccessible to small research groups in academia to have these kinds of resources to design chips like this. Chip design is not democratized due to this barrier of entry that has been created. So the question here is, why is this happening? The complexity of chips has increased when we go from left to right, but why does it need significantly more number of resources to design a chip like this? Well, the answer to that is simple. It's due to the challenges that exist in electronic design automation. And today I'm going to talk about 4 specific challenges. First is the is the scale problem or the problem of N in EDA. Most algorithms that perform synthesis, let's say place and route of transistors, verification and analysis of, of today's large circuits are all polynomial in N, or they have polynomial time complexity in N, where N is the number of transistors. So when we go from a billion transistors to a trillion transistors, and we have algorithms of quadratic or logarithmic complexity, that makes it very challenging for EDA tools to run. That brings me to my second challenge. Because of these polynomial time complexities, EDA tools have significantly large runtimes, and they've resulted in an increase in time to market. The third is a productivity challenge. Since most EDA tools are heuristic based and they often trade off speed for accuracy, they often require a lot of manual intervention, and expertise is required for high quality chip design to extract every ounce of performance. As a result, these chips, as a result of all these 3 challenges, we have this challenge of cost. And I'm not just talking about dollar cost, I'm talking about cost in terms of risk, expertise, which are all creating barriers to entry in designing chips like this. It's because of these very challenges listed here that we see pictures like this on the right and questions like this being asked. Has EDA failed to keep pace with Moore's law? And which, as an electronic design automation researcher, we should be ashamed to see. What this picture actually shows is that the cost of wafer pretty much always remains at a nickel or a dime per square millimeter. But this red curve here says that the cost of designing that same square millimeter is growing out of control. It's been a well lamented fact that we face a crisis of design. Taking innovative ideas into silicon runs head on into barriers of cost, risk, and expertise. My research aims to address these challenges by developing EDA tools that are ML based and open source based. The first ML based part addresses these first 3 challenges, while the open source part uh, indirectly addresses the first 3, but directly addresses the last challenge here. So I'm now going to talk about the role machine learning and open source has in EDA, and I'm going to talk about it using the Open Road project as an example. And this is a project that I've been involved with during my PhD, right from the start to the very end. And I'm still working with the Open Road project a little bit. The Open Road project itself is a large DARPA-funded project with folks from both academia and industry. The groups of folks involved are listed here. It has the goals of creating an open source EDA toolchain that takes RTL to GDS in 24 hours, no human in the loop. RTL itself is a high-level description of the hardware in Verilog, and GDS is a lower-level representation of the hardware in the form of rectangles that represent transistors and wires that actually ultimately go to the fab. So if you look at this picture on the left, the time it takes to go from top all the way bottom here in commercial designs in industry tools is of the order of several months. And when you think about this regime of 24 hours, no human in loop, without power performance area loss, there are several research challenges that need to be addressed to make such goals realizable. You need what Open Road calls these foundational technologies, which are first, extreme levels of partitioning, where you decompose the large circuit into these small bite-sized chunks. Second is the orchestration of distributed and parallel optimization of these bite-sized chunks. Third is machine learning to model and predict what will happen when a tool is run in a certain way on a certain design input. And the fourth is this notion of freedom from choice. That is, to be fully no human in the loop and lower barriers to entry, these tools will not have as many knobs as commercial EDA tools have, which can perhaps confuse a non-expert user or require the presence of a non-expert user to set in a certain way. Well, if you think about these four technologies together, the first two are already present in today's EDA tools. And despite that, today's commercial EDA tools take months to go from Verilog all the way down to GDS. So the important thing here is the second two foundational technologies that are defined here. So I'm going to remove these first two foundational technologies and leave these second two here. And the key uh, to reaching these goals of 24 hours, no human in the loop, no power performance area loss, is this notion of machine learning based EDA flows, especially when we live in this layer, in this world of restricted layout or freedom from choice. Overall, the Open Road project has been fairly successful. It's had several tape outs in a 130 nanometer technology. I think this number is over 600 right now. And we've also successfully taped out 12 nanometer GF12 um, SoC with about 500,000 instances with a 10-hour runtime. Well, it's not just the Open Road project or DARPA that has realized the value of AI and chip design in the recent past, but several companies such as Google, NVIDIA, Synopsys have all developed prototypes where they show how the success of AI has helped address several challenges where perhaps AI has helped improve designer productivity, address the scale problem to enable keeping pace, to enable us to keep pace with Moore's law. However, these companies have just touch the surface, and there's only a limit on how much academic groups and company can explore. They need significant help from academia to fully explore the benefits or perhaps the even harm of using machine learning in chip design. For example, Google has leveraged reinforcement learning to solve the macro placement problem. They require 6 hours of GPU runtime on a cluster of 16 GPUs, that is 96 hours of GPU runtime to perform placement of these 50 or 100 or macros to generate a placement that results in solutions that are better than commercial tools. This 100 macros is a really small design, and 96 hours of GPU time is a lot of runtime that not a lot of research groups can actually afford, and it falls back straight into that barrier of entry problem that I talked about earlier. So taking a look back at this picture, which I last time presented from the context of the Open Road project, but I now want to present it as a general IC design cycle. And I want to talk about some of the work that I did during my PhD. The research that we've done actually falls into all the problems highlighted in this red blocks, and it goes from timing analysis, IR drop analysis, electromigration analysis, and you can see those analysis tools interact with various stages of a physical design physical design flow that is shown here. So over the course of this presentation, I will be using this as an outline slide, and I will go over 3 examples of how machine learning has helped us in optimizing on-chip power delivery networks. I will talk about how machine learning has enabled us to perform fast analysis of temperature on chip or IR drop off chip or an analysis of power delivery networks. And the third, I will even talk about how machine learning itself can help us answer this bigger picture question of, where did the data come from that we very often hear when we say ML-based solution. So before I take a deep dive into the first problem, I'll pause here to see if there are any questions. Are there?
Yeah, so you're gonna approach this problem just with machine learning. You're claiming that machine learning will be the savior, right?
I'm on certain small problems with ML and EDA, traditional EDA algorithms working hand to hand together. That's what I'm claiming. So we can help, ML can help traditional EDA algorithms to perhaps improve runtime or to help better PPA generation, like power performance area generation.
Okay, thank you.
Excuse me, I have a question.
Sure.
Do you consider robustness as a major factor in VLSI design for your machine learning approach?
So when you say robustness, are you talking about reliability or?
Yes, reliability.
Uh, in the papers that I'm going to present today, none of them go over reliability. Okay, actually one does. We talk about how machine learning can help us do electromigration hotspot, and electromigration is a reliability phenomenon. So yes, in certain problems, and it's important to consider that. So in the papers that I'm presenting, one of them will talk about EM hotspot prediction.
Thank you so much.
Okay. So I'll now talk about how ML can help us optimize on-chip power grids. So to get an idea of how ML can be used, I'm going to switch gears a little bit to explain the problem of on-chip power delivery networks, and then I will get back to the ML problem. So the problem of power delivery network synthesis and optimization is that the goal, okay, let me step back a little bit. The goal of power delivery network synthesis and optimization is to deliver voltage from the outside of the chip to every single transistor on the chip. So this picture here shows a RISC-V core in a 12 nanometer FinFET technology, and the picture below shows a zoomed in version of the power grid. These blue, red, and pink and orange lines that you see here are power delivery network wires that carry voltage across all transistors in this area. This is a top level two-dimensional view of the layout, but if you look at this power grid in the third dimension, it looks somewhat like this. It's a set of wires that go across several layers of the BEOL stack, and the goal is to get voltage from outside of the chip down to every single transistor, where you can see it's represented as cell A here. So the goal is to get voltage from here down to every single transistor. So the power grid itself can be modeled as a set of resistances, capacitances, because wires in the power grid are parasitic, which are shown here. The bumps, which are the interface between the external parts of the chip and the internal parts of the chip, or you can think of them as IO pins, can be modeled as voltage sources that you see here. And the cells, which draw current whenever they switch, can be modeled as current sources that is seen on the side of the pic, that is seen on the bottom right of the slide here. So the goal, I'm going to repeat myself like a broken record, is to get voltage from outside, from here down to every single transistor on the chip without significant losses. And when I say losses, I mean two specific losses. The first is an IR drop, is an IR drop constraint, and the second is an electromigration constraint, where the goal is that the voltage at every cell must be greater than certain specified limits, and the current density, or the J wire that's represented here, must be less than certain specified limits. So both the voltage drop and the current density through these wires will depend on several factors. They will depend on the distribution of and values of these current sources below. They depend on the distance between the voltage source and the current source. They depend on how these resistors are actually distributed, or the topology of the power grid. If you have a lot more wires, you have more resistances in parallel, and you have lesser IR drop or voltage drop. So the PDN problem itself is quite complex, and estimating this IR drop voltage is significantly complex. Note that with the advancement of technology and miniaturization, designing a PDN that meets both these constraints is getting a lot more challenging due to small geometries of wires with large resistances and current densities. So in addition to that information, I want to talk about three challenges that exist in power delivery network design. So here is challenge one. Well, not only must PDNs meet IR drop and EM constraints, but they must also judiciously use routing resources. What I mean by that is that they must be good citizens and share routing resources with signal or clock wires. However, there exists a trade-off, and that trade-off is highlighted here. So if I had three different power grids that are shown in this picture here, the first power grid on the left uses a lot of wiring resources in the same area. The second power grid uses a little fewer wiring resources, and the third power grid uses the least number of wiring resources. So if you think about this, the power grid on the left has a lot of wires in parallel. Whenever you have parallel wires, you have parallel resistances, and power parallel resistances imply lesser IR drop. So this is good for IR drop, but this side is bad for IR drop. And on the other hand, this side on the left, when you have a lot of wires used, it's very bad for on-chip signal congestion. So you see a sad face here on congestion. And on the right, it's really good for congestion because you're using lesser number of wires and you have more space available for critical signal or clock wires. So there is this trade-off that exists in power delivery network design. And whenever you think of a trade-off, you think of an optimization problem. And that brings me to challenge 2. And optimization algorithms are typically very iterative. The optimization problem here states that what is the best power grid I should use such that I meet the electromigration constraints, IR drop constraints, while minimizing the number of routing resources I actually use. So if you think about that optimization problem, and if you think about a brute force implementation of that problem, if I am a PDN designer, I'm going to start at perhaps this end of the spectrum and say, okay, I'm going to first try this power grid. I'm going to choose this power grid. Then I will perform an analysis, which means I will solve for the voltage drop and current densities through the wires. It's usually done by solving a large system of equations, GV is equal to K, if you think about the problem algorithmically. And then I will check whether my constraints are met. Is my voltage at every cell greater than the specified voltage limits? And is my current density less than the specified limits? If yes, great, I have the correct PDN. If not, I go back and then instead of using this PDN, perhaps I use this PDN and I proceed and so on and so forth. Well, the problem seems simple enough, but it's not quite. There's a bottleneck. That bottleneck is really in analysis or solving the system of equations GV is equal to J. This is typically done using an algorithm called as modified nodal analysis. And this system of equations, GV is equal to J, has billions and billions of variables. And billions is quite an understated number, to be honest, because in today's industry scale designs, there are over hundreds of billions, to be clear. So for example, that 12 nanometer FinFET RISC-V core that we saw on the previous slide, it has about 12 million nodes. It's an academic design, so it's quite small compared to the industry designs. And it takes 3 hours of runtime just to solve this system of linear equations, GV is equal to J. And this is just the static case. It's not even considering capacitance for transients. So there is a bottleneck, and any optimization that calls this analysis under the hood is going to be extremely slow and prohibitive in terms of runtime. So the last and final challenge that I'm going to talk about before I come to how ML can be used is that this notion of how power grids are globally uniform. If you look at this power grid, it uses the same pitch across the entire chip area. When I say chip, I mean spacing between 2 adjacent wires. It uses the same pitch across the entire area. This power grid is designed to meet the worst case IR drop constraints, which are typically very local to a region, but the power grid is globally defined to meet those local worst case IR drop constraints. So what do I mean by that? If you look at this current map here, high current values are local to certain regions as shown by the red circle here. So if you build a power grid that is uniform across the entire design, you're over designing the power grid in those regions that are highlighted in green that don't have high demands of current. So instead of defining a power grid or designing a power grid that's uniform like this, can we design a power grid that actually has that looks somewhat like this, where you use higher wiring resources only in those regions that have high demands for current? This is the question this work tries to answer, is can we automatically design a power grid that meets the IR and EM constraints while using the least amount of routing resources automatically, right? Can we automatically design this power grid that looks somewhat like this? So to automate this problem, we've defined what we call as power delivery network templates in the chip. These power delivery network templates are structured, predefined building blocks of the power grid, which vary in their metal layer utilization and fit perfectly into the region of the chip. So the last time we looked at this picture, I presented this picture as, power grid 1, power grid 2, power grid 3. But now I'm going to present this picture as template 1, template 2, template 3, where a template fits perfectly into some region of the chip when this chip is, broken or tessellated into regions that are shown here. So if you go back to that optimization problem or the trade-off of which is the right PDN that uses minimal routing resources while still meeting IR drops and EM's constraints, and you have, tessellations or different regions, the question now boils down to assigning which template goes into which region of the chip. If you look at this problem of assigning templates to a region, it's something that we humans can try to do by looking at these two regions. For example, this is a region that has high current. Because it has high current, I'm going to use T1. This is a region that has low current, and because it has low current, I'm going to use T2. So it seems something very intuitive for a human to do, but in reality, for a machine learning, for a machine to do this, you can think it has about 3 possible templates per regions. And in this example, there are 36 different regions. So there are 1.5 e to the 17 different permutations and combinations of a power grid. And it's impossible for an optimization algorithm to exhaustively search this space and figure out what is the best power grid that uses least amount of routing resources while still meeting the IR and EM constraints. If you go back to this question and think about it from a which template goes where perspective, it's something that machine learning can help us solve. We don't have to exhaustively search this. In particular, a classification problem can help us, where the features are these images and distributions of current and congestion. The class is a template ID, T1, T2, T3, and then we can leverage CNNs to perform this classification because these two are essentially images, like your ImageNet or your AlexNet. So that way, we've created a mapping between, the power delivery network EDA problem and an ML problem. And that's one of the key points I really want to drive home, is to create this mapping to successfully apply machine learning algorithms that can help us address previously very runtime intensive optimization algorithms. So we've trained a machine learning model to actually predict which template goes into which region. And after running that machine learning model in inference mode, we were able to synthesize different templates in different regions. So for example, here, the picture on the left shows an integer number in every region of this chip. This integer number represents the template ID. This picture in the middle here shows these floating point numbers that are actually telling us how much wiring resources we've saved or how much improvement in congestion we have in terms of percentage. While these percentage numbers may look really small, 2%, 1%, in reality, it's 1% of thousands of routing resources that are in that region, the thousands of tracks of routing resources that are in region. So these are high numbers. And that synthesized template, while saving routing resources and improving congestion, also meets the worst case IR drop spec because the model has been trained to be aware of this. So overall, we evaluated this on several designs in our 12 nanometer, 65 nanometer technology, 50,000 to 500,000 instances, and the inference is really fast, right? It's less than 3 minutes, where most time is actually dominated by feature extraction. This is an open source available code. It's part of the OpenRoad project, and it's called OpenPDN, and the link is shown here. So that was the first problem that I wanted to talk about, and I'll stop here to see if there are any questions on the first problem.
Essentially, it looks like that the problem that you were trying to solve with, can you move back? Yeah, here.
Yeah.
This looks like vertex cover on the NP complete problem. It looks when you're trying to assign one of your templates on each one of those grids,
regions.
It's like a vertex cover, like NP complete problem.
Yes.
One question, can you go further on your slide? What does that negative 0.74 mean on that?
Here? Yeah. So it means that we've actually, so if I took a uniform power grid across the entire area that just meets the least amount of density while still meeting routing resources was template 1. So if I synthesized template 1 everywhere across this chip, then I'm going to have, I still meet IR drop, but I'm not going to be improving congestion in all these different regions. But it turned out the ML model actually told us that template 0 did a denser template here, which is why we use template 0. But in comparison, template 1 was slightly more sparser. So negative 0.7 means comparison to template 1, which was the baseline, we're actually using more routing resources in this particular region, but we've improved in the other regions. And it's very important to note that this particular region was not very congestion heavy to start with. The most congestion heavy regions are the ones highlighted in the red rectangles here. So that's where we had the most savings, because the idea was that the machine learning model can help us use neighboring regions because of its convolutional nature to leverage, on the adjacent region, I don't have that much congestion, so I can use my neighboring region to solve my IR drop problems in my current region. I hope that helps.
That's great. One more thing, you didn't tell us the type of machine learning you're using. Can you tell us something about the machine learning?
Sure. So the machine learning model that we used here is basically a convolutional neural network. This is a LayNet-based neural network model. So the way we did it is, first we generated a lot of data, ground truth training data. So we took different current maps from different chips, and we performed simulated annealing to generate that ground truth data, wherein we searched this space to figure out what is the best template for this particular chip. Then that is our ground truth data. We use that ground truth data to train the CNN. And once we have a trained CNN, given any new chip current and congestion map that comes in, we can perform a very fast prediction in less than 3 minutes to generate these templates.
I see. Okay, thank you.
Excuse me?
Sure.
I just wonder, while you're taking the ground truth, generating the ground truth of your data, you are using another ML approach, as far as I understand. Is there any tool or something that help you to generate the ground truth of?
Right. Yeah. So in reality, we would want to use commercial tools to help us generate the ground truth, but actually turns out there is no commercial tool that actually addresses the power delivery network optimization problem. You'll see in the next paper, in the next slide, in the next paper that I talk about, of how we've actually leveraged commercial tools to generate ground truth. I talked about simulated annealing to generate ground truth. That's an optimization algorithm. It's not an ML technique, but it's an optimization algorithm that can help us search this solution space to find, which is it minimizes the cost function of congestion while constraint optimization problem. It solves this constraint optimization problem that searches this solution space to find the most optimal solution.
Yeah, thank you. But it's a really good idea to use image processing and EDA technologies together. It's really brilliant idea. Yeah, thank you very much.
Okay, so I'm now going to move on to my second topic. So the first problem was in optimization of power delivery network, where the key idea was to create that mapping between EDA and ML world through this notion of PDN templates. The second problem is using machine learning to perform PDN analysis or estimate IR drop, and also perform thermal analysis. And I'll give an example of how we can create that mapping between ML world and the IR drop problem to help us speed up certain analysis. So we've already looked at all of this information on the slide before. In steady state, performing IR drop analysis or finding that voltage at every single cell below here maps on to solving the system of GV is equal to J of linear equations, which have billions of variables. We've already seen all of this before. Thermal analysis, another similar yet equally important analysis is actually thermal analysis. And thermal analysis is conventionally done by solving this partial differential equation shown on the screen here. So for a computer to solve this, it usually performs numerical integration techniques for transient analysis. And in steady state, this solution of this thermal equation also maps into a similar form of GT is equal to P. So since this is an FDM-based solution, the more variables you have or the more nodes you have, the more accurate your system is going to get. And this falls back into that, scale versus accuracy problem that I talked about, where the smaller number of nodes you have, the more slow your system is going to be to solve your finite elements. The smaller the size of your finite elements, the longer is the runtime of your tool to solve this system of equations, but the more accurate it's going to be. But the larger the size of your element, the less accurate, but the faster runtime. So there's a trade-off between runtime and accuracy. But the bottom line here is both these analyses are algorithmically very similar. In static state, they involve solving GV is equal to J or GT is equal to P for the thermal case. And in transient state, they involve solving partial differential equations that are shown here. Both these analyses are extremely expensive with hours and hours of runtime on industry scale design. You remember I talked about that 12 million nodes, 3 hours. It's of the order of, in industry scale design, some of these analyses take days together even. So on this slide, I presented a very equation heavy representation of, power delivery network analysis and thermal analysis. But on this slide, I'm going to present a more visual representation of the same problem. This is the thermal analysis problem here, where the input is a power distribution and the output is a two-dimensional distribution of temperature. Both these maps are correlated, but they're not identical. The correlation here is that a region with high power tends to also have high temperature, and a region with low power tends to have a lower temperature. It is this kind of relationship that a neural network can quite easily capture. In particular, we used this fully convolutional neural network for this problem by mapping the thermal analysis problem into an image-to-image translation task. In this particular problem, this unit has in ML actually, in the ML world, this unit has found tremendous success in performing image segmentation, where each pixel in the image must be classified to another pixel and which has a certain intensity value. In this particular case, for thermal analysis, we are classifying every single pixel on the power map to a specific intensity of temperature. An advantage this unit model provides us is that it's fully convolutional, which means that it has no fully connected layers in it. This makes the unit model independent of input image size, and being independent of the size of the input image is very important for chip design, for the fact that we want it to be independent of the area of the chip. That is, a network that is once trained on images or chips of a particular size should be able to transfer to other designs of different sizes. So the key idea here was to map the static analysis problem into an image-to-image translation task, and then train it with significant amount of ground truth that has been generated from commercial tools. So in this particular case, we used ANSYS's IcePack to generate these images on the right. We gave in power maps and we got in these temperature maps. And once we had this ground truth across hundreds of designs, I think it was 120 to be specific, we trained this unit model to perform this prediction quickly. So this was for the static case. For the transient problem, the input is a time varying series of power distribution, which you can think of as a power video. And the output is a video of temperature or a two-dimensional time series distribution of temperature or a video of temperature. And when you think about this problem, it's like a video to video translation task or a sequence of power maps to sequence of temperature maps translation task. And the core architecture that we use to solve this sequence to sequence translation is an encoder and decoder like architecture that is very similar to the architecture we saw on the previous slide with the unit, except that here we use LSTM cells, long short-term memories, to actually model that time varying component, or the fact that it has certain memory, where the temperature at a particular time instance depends on the power distribution at that time instance and previous n time instances. So we mapped this into an LSTM-based network to solve the sequence to sequence translation task. And we did a very similar approach. We generated ground truth from IcePack. This is the ground truth that's generated from IcePack. We used several input power distributions and generated several ground truths. And then we trained this model that's shown on the right top corner. And we found that our prediction, we on an unseen test case, that is, this particular test case was not given to the model during training, was been able to predict temperature to very high accuracy. If I remember correctly, there was about 5 degrees of error between these two cases, and 5 degrees out of a max of 150-degree temperature is not much. To generate this ground truth, it took us 2 hours of runtime to go from here to here using commercial tools, but to go from here to here using ML was down to a few milliseconds because it's just a fast ML inference. So conventionally, we brought down these hours of runtimes just a few milliseconds. We did this on both thermal analysis and IR drop analysis and even electromigration hotspot detection. But I've just talked about the thermal analysis case here. The concept is the same across the other two analyses as well. So that was a really quick summary, but the key message is to create a mapping between the ML world problem and the EDA world problem. In the first case, we did it through those PDN templates. In the second case, we did it through image to image and sequence to sequence translation tasks. So I'll stop here to see if there are any questions before I move to my final topic for the day.
If they
Okay.
have, they can
Sure.
ask at the
Ask at the end. Yeah, okay, sure. So for the third topic, I'm going to talk a little bit about how machine learning can help us generate data itself. So in the top two examples, I talked about ML techniques for PDN, right? And whenever we talk about using ML, a lot of people ask, where did the data come from? So in this particular problem, I'm going to talk about how machine learning can help us generate benchmarks to evaluate our EDA tools itself. And it can help answer that question of where did the data come from. So the availability of data and compute power has been one of the driving forces behind advances in AI. Data-driven models are bringing a revolution to the world. They are transforming our lives in the form of self-driving cars, face and voice recognition, medical diagnostics, and many other applications. For the successful application of AI or ML to chip design, we really need sufficient data that's open source and benchmarks that are open source to actually evaluate our research and drive advances in EDA or electronic design automation or even chip design for that matter. However, data and benchmarks for chips are very hard to find. And why is that? Well, 3 reasons. The first is technology and design IP. And when I say technology and design IP, I'm talking about how we don't have access to, let's say, the latest and greatest TSMC, the 4 or 3 nanometer, or we have to literally sign away our lives in NDAs to get access to that, or we don't have design IP, where we don't have access to see how Intel CPU or an NVIDIA GPU or an AMD processor looks like today, because it's all hidden behind our intellectual property. The second challenge is this challenge of rapidly changing technology with scaling, where where with every 2 years, there's a new process that comes out, and creating benchmarks in that new process requires significant amount of volunteer effort to release benchmarks in a particular technology and then even update that with coming technology trends. For example, we moved from MOSFET to FinFET, and we need to have all the benchmarks that were previously released as planar transistors to today being representing FinFET transistors. And it actually requires a volunteer effort from a company. Let's say today an industry, somebody in the industry decides that, hey, we need to help out academia a little bit by releasing these benchmarks. They do it primarily out of goodwill. So it requires volunteer effort, and it involves significant amount of laborious volunteer effort to not only release those benchmarks, but also maintain those benchmarks with advances in technology. So one such example was the IBM benchmarks that were released for the Power Grid, IBM Power Grid benchmarks. And these benchmarks released current maps. If you noticed, both my first topics were about having current distributions or power distributions. So IBM released these current map benchmarks in 2007 to drive research in the area of power delivery network design. This current map is a key component for all the ML applications that I previously saw. So I will now talk about how these current maps actually fall back into these 3 challenges. These current maps were released in 2007. updated once in 2008 and haven't been updated since, which means they represent old technology nodes and they don't represent the challenges that we see today, which means they are really old and they fall into this challenge of rapidly changing technology with scaling. Two, they are quite unrealistic. If you remember the current maps I showed on the previous slide, they didn't look anything like this picture shown here. This picture here shows these block-wise region uniform current maps, when in reality, current maps are look quite different. They have released these current maps like this because they want to hide away IP. For example, they don't want to show placement locations or IP related to that design. So they release it in this particular fashion. The third reason is that because it requires a lot of manual effort to release these benchmarks, there were very few of these benchmarks released. There are about less than 10 IBM Power Grid benchmarks, and in tens of counts of number of tens of benchmarks are nowhere near sufficient to do any of the ML applications that we talked about. We need hundreds to thousands of benchmarks to actually apply ML techniques for data. So this is the picture of what a real current map looks like. I should have brought that up a little earlier. So this work that I'm going to talk about proposes BGAN, which is an ML-based methodology for generation of realistic yet synthetic power delivery network benchmarks. The idea is motivated by the success GANs, or generative adversarial networks, have had in generating images of faces which are synthetic yet realistic looking that you saw in this video here. The goal of BGAN is to generate several synthetic yet realistic looking current and power distributions, as you see on the right. Current distributions are critical to advancing EDA research for power delivery network problems that you saw in the previous two topics that I talked about. So the idea was motivated by using by leveraging the advances GANs have had in the generation of fake images, to use GANs to generate fake yet realistic looking current maps. So due to the shortage in available real circuit data, the key challenge really lies in training this GAN. If we had sufficient real circuit data to trail the GAN itself, then the whole point of this work is like null and moot, right? So the key challenge is really in generating data to train the GAN. And one way to approach this when you have a really small data set is to use this technique called as transfer learning between a source and a target data set. The idea is that you train the GAN in a source data set that is different from the target data set, but there's a lot of available data in the source data set. And then you fine tune the weights of that GAN using the limited finite real circuit data that you have available. However, the key challenge is to ensure that the source data set and the target data set share similar key characteristics. So what we found that this is the way, this is how a current power map looks like. And we tried to identify the key characteristics of the power map so that we can find a corresponding source data set which has the same characteristics. So if you look at this power map here, you have these rectangular regions that represent macros or blocks within your chip. You have certain power or current hotspots that are shown here. And you have these Manhattan geometries that represent either wires, or they represent, channels between these blocks of macros. So observing this, we found that urban satellite images have very similar characteristic traits between with the current map. For example, these macros can be mapped onto building tops. The Manhattan geometries or macro channels can be mapped onto Manhattan road networks. And the hotspots can be mapped onto trees. Therefore, we used these urban satellite images as the source data set to train a GAN that looks somewhat like this. It has a lot of layers and a lot of meters. But once we trained the GAN in the source data set, we then used a handful of real current maps and we fine-tuned those weights, fine-tuned the weights of the GAN in a transfer learning technique. So using that approach, we were able to generate thousands of fake yet realistic looking current maps, and 8 of such current maps are shown on the screen here. They share very similar characteristics as the original maps, which can be seen both visually, but we also had several metrics in the paper to actually measure quantitatively how similar they were. And these current maps have also been released to GitHub on this link shown here. and they're called as BGAN benchmarks, and they have both current maps and their synthesized power delivery networks with the IR drop distributions released there. So to conclude, over the course of this presentation, I gave 3 examples of how ML can help EDA. In particular, I talked about the power delivery network problem. My research spans different areas of that physical design flow, but I just focused on power grids and thermal and benchmark generation for PDN because it's really easy for me to have that presentation without having to redefine different nomenclature in a different problem. But overall, ML really enables to take out the guesswork from IC design, where we don't have to guess which is going to be the best power grid for this design. It helps us with fast turnaround times, because remember, we brought down those hours of runtime of PDN analysis down to a few milliseconds. And it also helps us with fast optimizations for better power performance area. And it takes out that guesswork that I talked about. Most of these 3 topics that I talked about today have easy to use tools and open source repositories on GitHub. That's pretty much all that I want to talk about today. So thank you very much. I'll be happy to take any questions in the rest of the time that we have left.